Hi, I'm Roy Mutalik, Application Engineer with DesignPoint, and as an engineer, I'm always curious about things that I don't know the answer to, don't really understand. So today, I'm going to take you through solving one of the problems of something I just came across in my life that I wanted to understand a little bit further. So I'll start with a little bit of a backstory here. I recently just purchased a new home, and one of the perks that came with that is I now have a really nice kitchen to work with. And I've always enjoyed cooking, and I've been doing a lot more as a result of that. You know, baking some cookies, making steaks, doing pot roast, all kinds of stuff. And it got me thinking about something I know that you've all experienced. So when you heat up your oven, you've got a nice hot volume of air in there that you're using to cook. When you open the door to that oven, you're going to feel a rush of hot air coming out. It kind of hits you in the face, and I always imagine it kind of goes up and makes a plume and hits the ceiling. And I wanted to understand that effect a little bit more, understand sort of what's going on there. And it got me thinking about one other thing as well. You know, we've all heard the old saying, if you can't stand the heat, get out of the kitchen. Well, I wanted to quantify that a little bit. When you open that oven, how much does it actually heat up your kitchen? So let's dive in and see if we can take a look at those two. I'm going to be solving both of these problems today. Again, the initial opening of that oven and seeing that plume, understanding what that looks like, as well as seeing how much the temperature in the kitchen itself rises. And I'm able to do this using a computational fluid dynamics simulation right within my CAD tools that I have handy here. So without further ado, let's dive right into the CAD tools here. I'm going to jump over to SOLIDWORKS here. SOLIDWORKS is a great tool to allow me to quickly model a mock-up of my kitchen, which is what we're seeing on screen here. I just made a small room here, and within that I have my oven itself there, and a couple of other little pieces. I put a smoke detector up on the ceiling, you might notice right here, and that's going to allow me to track the temperature sort of up at the ceiling there. That'll be an important piece to look at as that plume comes up and hits that there. One other quick piece here I'll just share with you. I also modeled in here a solid body to represent the volume of hot air that's in that oven at the starting point there. And I'll show you why I did that in just a moment here. So the model itself is very simple. Let's dive right over to SOLIDWORKS Flow simulation, where I'll be able to set up that computational fluid dynamics simulation. SOLIDWORKS Flow Simulation is great with it being integrated right within SOLIDWORKS because I can quickly iterate between validating my design and adjusting it. I'll just go ahead and set up a study with us here really quickly. Clicking through the prescribed menus here in this wizard makes it very easy to select my unit system and all of the parameters that I need. At this screen, I'm going to enable a couple of different options here. So I want to make sure that this study incorporates gravity, and that's how we're going to see that hot air rising, that effect occurring. So we'll specify that and make sure the direction is pointing the correct way. I'm also going to tell Flow Simulation that this is a time-dependent study. So what I'm setting up here is at t equal to 0, I'm going to open that oven. And I want to see over, let's say, the next 4 seconds, what happens as that hot air is starting to rise and make its way out. So I'll key in those parameters here. 4 seconds of total analysis time, and maybe we'll look at the results every 0.05 seconds. That's going to be our time step. I'll go ahead and hit next here. I can very easily select from my predefined libraries within Flow Simulation which gases I'm using here. In this case, air. 350 degree air in the oven and 68 degree air outside of that oven. I'll continue to make my way through these menus here, the predefined libraries, and just setting up my study defaults here. There's one last initial condition I'm going to put in here. I heat my home to 68 degrees Fahrenheit, so I'll key that in as the ambient temperature in the room. We'll go ahead and hit finish here, and that'll actually create the study. Now a study like this is actually relatively simple to set up. We just need one initial condition on that volume of air internal to the oven here to say that it's at 350 degrees. So we'll specify that. I do so by selecting, in this case, that solid that I created, which represents that volume of hot air. And I'm going to use a checkbox right here to disable the solid component. And that's how we tell SOLIDWORKS this isn't actually a solid, it's a volume of air. I'll key in here the temperature of 350 degrees Fahrenheit. And I'll leave all other thermodynamic parameters their defaults. So at this point, our study is really set up. It's ready to go. But I'm going to add one more item to it really quickly here. I wanted to track the temperature at that smoke detector, and I can do so using something called a goal. A goal is basically a way of just telling SOLIDWORKS Flow Simulation, hey, this is something important that I'm going to want to look at. So I'll select that face here, and I'm going to tell FlowSim that I want to capture maybe the maximum temperature of fluid around that face. I'll be able to really get some nice plots on that and understand what's happening to the temperature at that location. At this point, I'm actually ready to run my study. So I'd go up here and hit the run. These simulations can take just a couple of minutes to run, so in this case, I'm going to just go ahead and activate a completed study I already ran. And I'll go ahead and make sure to load my results for it here. We can start to interpret the results in a couple of different ways. The first point, the results are dependent on time. You remember I selected that time-dependent option. So what that means is I want to look at any given time moment. So let's go ahead and select to look at t equal to 0. And what I'm going to show here on screen is something called a cut plot, where it's taking a slice through the model and showing the temperature of that fluid. I'll just go ahead and hide my geometry so it's easier to understand what's going on here. What we'll notice here is the plot is showing exactly what we'd expect. At t equal to 0, right before you open the door to that oven, we see the fluid internal to the oven is at 350 degrees, and the fluid outside the oven is at 68 degrees. And now, over the next 4 seconds, we're going to see those two start to mix. So let's jump ahead a little bit here. I'm going to load a time moment of maybe half a second later. So we'll grab right there. And now what we'll see is, after half a second, that hot fluid inside the oven is starting to make its way out. If I jump ahead a little bit further here, maybe we go to 1 second, we'll really start to see that plume developing here, as that hot air is kind of rushing its way out and making its way up towards the ceiling. And if I jump ahead even further here, maybe in this case to about 3 seconds, we'll really be able to see that plume has developed here, and it's actually hitting the ceiling and starting to disperse. So this is great for being able to see at a snapshot in time. But what if I want to see across all 4 seconds sort of what happened? Well, it's really easy to do that with an animation. In this case, I've defined an animation here, just saying that over 10 seconds of physical time, I want you to animate for me all of the plots of the cut plot of temperature here. And I can very easily output that result to a GIF file or an AVI, a video file itself. So really convenient to do. This was just defined using this animation wizard right here. I'll show you the result here really quickly. And this is what we see across 4 seconds of results, animation of that plume making its way out of the oven, kind of going up, hitting that ceiling, hitting that smoke detector, and dispersing from there. So again, a great way to kind of graphically understand really what's happening. And in this case, sort of what I expected is correct, that it is a plume that's going up and it's hitting that ceiling. So let's talk about that smoke detector. Looks like it's getting hit dead on here with that hot air. What's happening around there? Well, we can track that with that goal plot that I defined. So I'll jump back to SOLIDWORKS Flow Simulation here, and I can very easily define a goal plot. I'll tell it here that I want to track the goal that I created on that smoke detector across physical time. And from here, it's very easy to even show it on screen or export it to a Excel spreadsheet, including all the data points that can really easily be plotted. So I'll show you that result here. This is what my temperature at smoke detector plot looks like. I just exported it to Excel and then pasted it right here. So we can see at t equal to 0, that temperature is at 68 degrees. And then at somewhere around 2.5 seconds, that plume starts to hit it and it actually heats up until it reaches a maximum of about 179 degrees just before 2 seconds here. And then it starts to kind of taper off from there and makes its way back down as that plume disperses. So really great in giving me that insight about what temperature is that smoke detector actually feeling as a result of that plume. So this effectively answers that first question. What does that plume really look like when it's going up, and what's happening at that smoke detector? But we still want to address one other piece to it, which is what happens to the overall temperature of the room as a result of having opened this oven. And the great news is that by just changing a couple of parameters in my flow simulation study, I'm able to achieve that result and see what happens to that temperature. I've created a second study here, which was a duplicate of that first one, and I've only changed 2 parameters really in here. First, in the calculation options here, rather than calculating for only 4 seconds, I want to look at after a little bit more time has passed. So I chose 300 seconds. After you've kind of opened that oven and it's dispersed and it's allowed that fluid to mix a little bit, we want to track the temperature at that point after some time has passed. So I simply put that physical time to 300 seconds here, and I even told it here that now I can just look at results every 1 second. We don't need it every 0.05 seconds. I just defined one other item here, and that is another goal. So instead of tracking the temperature at the smoke detector itself, which will show me that spike again, maybe we wanted to track the temperature at the back wall. So something that'll give me a little bit more of an average result. So I asked Flow Simulation to track that this time. What is the average temperature on that back wall over here? And we can go ahead and run this study. Again, it takes just a couple of minutes to run, so I'll go ahead and load my results here. And just the same way, I'd be able to look at the same cut plots as well as I saw in the first study. In this particular case, I'm really concerned with that goal plot and seeing what happens to the temperature. So let's jump over and take a look at that here. And sure enough, here was the output of the average temperature of the back wall. So what we see here, again, at t equal to 0, it started at 68 degrees here. And it looks like when that plume initially started to hit it here, it kind of spiked a little bit. And then it oscillates here as it kind of makes its way down and eventually achieves kind of a close to steady state result here. After 300 seconds, it's 72.4 degrees Fahrenheit as the average temperature on that back wall. So what we see just from opening this oven once, we're seeing a temperature increase of about 4.5 degrees. So that's fairly significant. Of course, this is a pretty small kitchen that I've modeled here, but again, fairly significant result. Certainly not what I would have expected. So I'm sure we all know the old saying, if you can't stand the heat, get out of the kitchen. And what that means to say is, if you can't take the pressure, if you can't solve that problem, get out of the way so that somebody else can. Well, in this case, we were able to solve that problem thanks to SOLIDWORKS Flow Simulation. I want to thank you for your time. I hope you found this presentation interesting. If you have further questions, please visit us at www.design-point.com, or you can email us at info@design-point.com. And definitely connect with us on social media. We're on Facebook, LinkedIn, Twitter, and YouTube. Again, my name is Roy Mutalik with DesignPoint. Thank you so much.